I don't really like T of t. They could have used any other notation. It's confusing. It could be confusing. Negative 0.1 t squared plus 1.2 t plus 98.6. And they are giving us the interval 0 to 12 for t. Okay. T is the temperature, is in Fahrenheit, and T is number of days. So T, lowercase t, is in day, measured in days after the onset of it. Okay, find the relative extrema and sketch a graph of the function. Perfect. Now, this situation is not a complicated situation because this is quadratic. Okay, it has a negative leading coefficient, so we know that it will look like this. But this is just for our peace of mind, so to speak. But we have to apply the calculus procedures. But I already know that it has to have a maximum. I'm only asked to graph it between 0 and 12. I know how to find algebraically how to find the maximum, but I have to apply the calculus procedures. So I have to find the first derivative, and I get negative 0.2 t plus 12, plus 1.2, sorry. Okay. This is a linear function. It could never be undefined, so it will never be undefined. Because remember, I always have to look for critical numbers coming from both sources. But it could be 0. T prime of t could be 0. Linear, so negative 0.2 t equals negative 1.2 when I move it to the other side. So t equals 12 divided by 2, so t equals 6. Now, when I present the table, so I have t prime of t and t of t, and if I want a second derivative, if I need it, then I only have to show this interval because they specifically tell us don't look anywhere else. There is no need because t's in days, there is no point in going from negative infinity to infinity because I cannot have negative infinity days or negative 5 days. So this is specifically given to us. So I have 6 here, and I know that the first derivative is 0. I study the sign of the first derivative. So when I plug in 0, it's obviously positive, and on the other side will be negative. Now all I need to do now is plug in the original function 0 and get a number here, plug in the original function 6 and get a number here, and the original function and get those numbers. If I want to calculate the second derivative is negative 0.2, and it makes sense. I know the graph. It opens downward. So therefore, the second derivative has to be negative, and it is. So all checks out. It's just that I have to show the work using calculus. So now I will put in the graphing calculator. I have it ready. I will put this function in the graphing calculator because I need the y coordinates of these x values. So I'm going to share my screen and go to y equals, clear, whatever you have. Put in this function, negative 0.01 t squared, and then plus 1.2 t, and then plus 98.6. And now I just need 3 values. I want 0, and of course that would be 98.6. I want 6, and that's 105.44. And I also want 12, and that is 111.56. And remember, these are degrees Fahrenheit. Now at this point, I have to make sure that these 2 rows work well together, because if they don't, I'll say, oops, stop, something is wrong. So from 98 to 105, the function is increasing, and that's exactly what the first derivative tells us. We know that when the first derivative is positive, the function is increasing. From 105 to 111, so something is wrong. Because from 105 to 115, 111, it doesn't go down. So let's see what I did. Now it's very clear. I have to show that it's decreasing according to this, but it's not decreasing. From 105, I copied something wrongly, I entered something wrongly, and I know to say stop. Something is not right. Let's see what I did. Let's see how I entered the function. Ah, very clear. Now I know. Now I know what I did. So everything is wrong because I didn't enter the function correctly. It was negative 0.1, not 0.01. X squared plus 1.2. Now, let's say I have to start from scratch. 0 is still okay. 6. 6 is 102.2. So I made a boo-boo by not entering the function correctly. But the table saved me. The table told me, hey, madame, you're off. Terribly off. Good. So now the numbers are, one more time, so 102.2 and 98.6. Okay, now I start again. So from 98.6 to 102, yes, that's correct. From 102 to 98, yes, now it makes sense. Obviously 100, I couldn't write it right here. I'll have to write it again when it dries out. So I know it's clear that this is a local max, as I expected, and this is it. So now when I graph, that's what I need to graph. I will graph this point, I will graph this point, I will graph this point. I don't need anything else. I'm not allowed to graph anything else because we are given, trust me, the table will always save you, like it saved me. So here it is. So I see that the function values go from 98.6 back to 98.6 with a maximum of 102. So what I can do, break the y coordinate and say this is 90, this is 100, this is 110. That's all I care about. And here I have 2, 4, 6, 8, 10, 12. Good. So at 0, let me see if I can use a different color. At 0 is 98.6. At 6 is 102. And back here. That's all I need. And that's it. So here's the graph. If you want to graph it with a graphing calculator, you can. So I have to write the graph here. So it's t of t, negative 0.1 t squared plus 1.2 t plus 98.6. So if you want to check and graph it with a graphing calculator, that's fine. So here it is. But you have to adjust the viewing window accordingly, otherwise you're not going to see anything. So x minimum, 90. I'm sorry, I meant 0. 0 to 12 with a scale of 2 or 3, doesn't matter. Y minimum, 90. With Y maximum, let's say 110 or 115, it doesn't matter, with a scale of 30. Now I will see this graph exactly as expected. Good. George, is this better?
Yes, very helpful.
Any questions here on any of the steps? Anybody?
So the second derivative will always tell us which way the parabola opens.
Yes. If it's negative, it opens downward. If it's positive, it'll open upward. If the second derivative can be 0, the function may have an inflection point. It may. 0 or undefined. Very good. Anything else? Anybody else? Any questions on this or any other? Okay, so let's move on to another question, or we will continue. Okay. Where am I? Here. I was trying to get to, very good question, thank you. 315. So I was thinking to look at this problem. Let's read it. See if you think that we should work on it. Minimizing cost of materials. We have the cost. They're giving us the function. And here's the function. X is the length of one side of the field. Find the values of X, values of X, which for which the cost to build the fence is minimized. So we are given a function, and they're asking us to find the minimum. And what is the cost? In other words, what is the value of the minimum? Part A tells us or asks us what X creates the minimum, and part B, find it. Find the minimum. Is this something we want to look at? Okay, perfect. Let's work on it. So this is problem 57 on 315. And we have C of X equals 8X plus 12,000 over X. Okay. Since C is the cost, and X is the length, obviously we're going to start at 0, but not even at 0, because why? I cannot even start at 0. If the length is 0, then I have no cost. And also 12 over X does not exist. Okay, so they're giving us this function. They're asking us find the minimum. What do I have to do first? What do I have to find? Of course, it's not infinity, but you know what I mean. What do we need to find first? Since it's asking us for a max and min, there is no really need of the second derivative, because they only want us to find max min. They're not asking us to graph the function. They're not asking us to find concavity, inflection points. So what do I have to find first?
The first derivative?
Absolutely. Now, please remember, when we differentiate 1 over x, does anyone remember what does this equal to? Because this is a very important situation. We should
1
know.
over x squared.
But negative, indeed.
Oh, negative.
Yes, indeed. This is very important, especially later on when we move on to chapter 4. Before I forget, we do not meet next week. Next week is a spring break. Okay, good. So when I differentiate and get C prime, this is easy. This is just 8, right? But then minus 12,000 doesn't go anywhere, divided by x squared, as you just said, as George just told us. But now, remember, I have to find the least common denominator. And there is only one denominator, but I need to multiply this by x squared. So 8x squared minus 12,000. Good. I found the derivative. Now what? The steps are very important. That's why I sound like a broken record. So somebody can tell us what will be the next step. So I have the derivative. Now what do I do next? I need to
set it equal to 0.
Yes, or undefined, because we are trying to find the critical numbers. Yes. So the first step is find the first derivative. The second step is find critical numbers. And as we know, critical numbers come from two sources, either c prime of x being undefined, but it's undefined for what x? What is the x for which this is undefined?
When x is 0.
Right, but so is the function. So that cannot be a critical number. A critical number requires c prime being undefined, where c is defined. But c prime is undefined at 0, but so is c. So there are no critical numbers coming from c prime being undefined. But yes, we have critical numbers coming from c prime equals 0. So I'll say here, no. A fraction is 0 only when
The top equals 0.
excellent, thank you so much. So I have 8x squared minus 12,000 equals 0. I move 12,000 and I divide by 8. So when I divide 12,000 by 8, what do I get? Lazy people, use a calculator. I mean, I should simplify it, but that's not the scope of what we're doing here. So 1,500. Okay, perfect. Good. So then I have several options. And I think the best one is this. Although it's quadratic and you have to write plus or minus, I will not, in this case, consider plus or minus solutions because I can have the length of a side as a negative number, right? But I have to write it because that's the correct answer, at least the partial answer. So then when we take the square root, so the square root of the previous answer, okay, it's 38.7. I'm going to round it up to 39. So 39, I forgot what it was. They were giving us the measurement unit in what? In meters, okay. And of course, I'm going to cross it out and I'm just going to say only 39. So I put 39 in the table. I put 0. I have to study the sign. But remember, the denominator is always positive. I'm not going to waste my time to plug in anything in x squared. It will be a waste of time. But when I plug in 0, in the numerator, I get negative. So on this side is negative, and on the other side, when you plug in any number you want to the right-hand side of 39, you will see it's positive. But now I need to determine this value because I will not know what is the absolute minimum here, right? So you can also check, just to make sure that the signs are correct, you can also check, let's say, with 10. I'm not going to put them in the table. I'm not going to graph anything anyway. And 50, just to make sure that these numbers are higher than this number, and this one is lower, right? This is higher than this because it's coming down, and this is greater than this. Okay, so I'm going to go back to the calculator, and I am going to put in c of x, clear everything else, 8x, and plus 12,000 divided by x. And all I need is just to check my work. I'm going to put a number like 10. I need to put in 39. And I'm going to put 50. And they better work. So the minimum, the absolute minimum should be roughly 620. So to the left, I have 1280, which is great because it decreases to 620. And on the other side, I have to have a number greater than 620, and I do. So I checked. It really is going down and then up. And I found the absolute minimum. So the minimum cost is when the side X is 39 meters, and the minimum, of course, rounded, approximately 39 meters, and the total cost. Okay? In dollars. Does it make sense? Is this okay? So these are applications of differentiation. So if you remember when we started chapter 3, I said this chapter deals with more and more and more applications. So let's summarize what we know so far. So in chapter 3, we looked at graphing. Why was differentiation so important here?